There are some more complicated trig identities that require some more sophisticated strategies to prove them. Sometimes they involve negative angles. So I just want to say a quick thing. Here's theta, and the coordinates at this point are cosine theta, sine theta. Now, negative theta would be going in the opposite direction. So this point here is cosine negative theta, comma sine negative theta. But notice that the x-coordinates are actually the same because they're on the same vertical line there. So we can say that cosine negative theta is actually equal to cosine theta. And that's a new sort of ninth trig identity to add to our list of 8. On the other hand, sine theta and sine negative theta are not the same number because one's, in this case, positive, the other's negative. So we can say that sine of negative theta is the opposite, so it's negative sine theta. So this is like a trig identity number 9 and 10 to add to the other 8. So here's an involved looking trig identity. And I'm going to work with this left-hand side. The reason I'm going to work, and I'm going to see if I can get it to equal the right-hand side. What I'm noticing about the left-hand side is that it's a fraction, and there's this plus sign here. So just like you can add together fractions with common denominators, you can also, like if I have a over b plus c over b is a plus c over b. Well, you can also go in the opposite direction. If you have a plus c over b, you can split it up into a over b. Normally we don't do that. Normally we go in this direction, but we can go in the other direction if it helps us. So let's take a look at what would happen if I did that. I would get 1 over cosine plus cosine over cosine. I'm not going to worry about the right-hand side. I'm going to just write RHS for right-hand side. Now 1 over cosine is the same thing as secant. Cosine over cosine is 1. Now I'll start looking at the right-hand side, because the left-hand side is about as simplified as it can get. I see this tan squared theta. Well, that's one of the identities. Tan squared theta, the identity is 1 plus tan squared equals secant squared. So that means that tan squared is also secant squared theta minus 1. And now we use the trick where we factor the secant squared minus 1. So secant theta minus 1, secant theta plus 1, and now it's all coming together because the secant theta minus 1's cancel out, and this left side and right side are equivalent. We can change this question mark into a nice check mark. Pretty involved trig identity, actually. In a trig identity, we simplify one side or both sides until they look like each other. We don't do algebra. We don't sort of combine the sides. Like, it's very tempting in this question to want to cross-multiply, because cross-multiplying would, if we were allowed to do it, would answer this question very fast. But we're just not allowed to do that. But there is a strategy. If you ever notice a numerator or denominator with like a 1 minus cosine theta like that, or a 1 plus cosine theta like that, we have an identity with, like, we have 1 minus cosine squared equals sine squared, and we can use that. If this thing was just a squared, that would be really nice, but it's not. But we can make it into one by multiplying the numerator and the denominator of the left-hand side, just like the opposite of when we factor it, we're actually introducing a 1 plus cosine theta to the numerator and denominator. Let's see what that accomplishes. The denominator becomes 1 minus cosine squared theta, which is great because that's an identity. Sine squared theta. The numerator becomes, actually I'm not going to distribute through, I'm going to leave it 1 plus cosine theta if I didn't leave it, I'd have to factor it out anyway, because now this sine theta can cancel out with one of these, and I get 1 plus cosine theta over sine theta, which actually is equal to the right hand side. This can be turned into a check. So that's a sneaky trick to multiply numerator and denominator by 1 plus cosine theta, anticipating this turning into 1 minus cosine squared theta, which can be replaced. I'll use that trick again with this one. If I multiply, see I have 1 minus sine z, I can't do much with that. We can't split it up like we did when the expression was in the numerator. But if I multiply numerator and denominator by 1 plus sine z, equals right hand side, I hope. This becomes 1 minus sine squared z. 1 plus sine z is the numerator, equals, I hope, right hand side. And this turns into 1 plus sine z over cosine squared z. Now this is resembling the first question where I have this fraction now. You see the plus is in the numerator. If the plus is in the numerator, 1 over cosine squared z plus sine z over cosine squared z. Start looking to the right and I see already this 1 over cosine squared, I'll just go like that, can turn into secant squared z. And I look now at this sine z over cosine squared z and this tan z secant z, and I see I can also split up, I can change this cosine squared z into just cosine cosine. That way I would have cosine z equals, I hope, right hand side. And now we're finished, because the sine over cosine turns into tangent z, and this 1 over cosine turns into secant z. So those are some other tricks. This last one utilized both the multiplying top and bottom, if it's a minus here, by 1 plus sine z, 1 over 1 plus sine z, and then at the end of that problem, the trick of splitting it up. You can't split up originally, but you can split it up when it's the numerator that has the plus or the minus in it.